Jackson. In our previous video, we worked some of these problems up here, 9 through 14, where we were working on antiderivative problems, or families of antiderivatives, where we had to do substitution. In this video, we're going to try to do problems 15, 16, and 17, which also requires to find antiderivatives where we do a substitution. But this time we're going to use that in the Fundamental Theorem of Calculus to actually compute a definite integral. Now here we're wanting to find exact values of these definite integrals, and we're going to find exact values and approximate values here, and we're going to check them with our calculator using, or at least I'll let you check them on your calculator with a numerical integration program. But here what we want to do is actually use the fundamental theorem and use substitution to work these out. So, we're going to work these three problems. I'd like you to work them yourself first though, so please write these down, try to work them out, come back and check your answer. So let's start with number 15. Press pause now. Okay, now you're back. Hopefully you've worked these. So let's start with number 15 now. So number 15 says we have the integral from 0 to 3 of x to the third times 3 plus x to the fourth all to the sixth. Alright, well, it looks kind of messy, but actually turns out to not be too bad. What we do is we have a variable base and a constant exponent. When you have that situation, you typically want to let u be the variable base. Or at the very least, that's something we're going to try. So we let u be the 3 plus x to the 4. So I write that down next. I don't have any of this here yet. I write that down. Now I find the derivative. Well, the derivative of 3 is 0. The derivative of x to the fourth is 4x cubed. And then, of course, we always have our dx here. So du is du over dx times dx. Du over dx, of course, is 4x cubed, but then we have our dx. Okay, well, let's see if this is going to work out. Well, we can certainly take this part here, the 3 plus x to the fourth, and replace it by u. So this part is going to become u to the sixth. The question is, can we get our du? And that's always the tricky part to see if that's going to work out. Well, we have our dx, certainly. And we do have, luckily, we have the x cubed. We don't have the 4, but that's not a problem. We can fix that by just sticking a 4 in here. Multiplying by 4, as long as we multiply by 1/4 right in here, but that can be brought out to the front. So this 1/4 out front balances with this 4. If you multiply that back out and reorder, you're back where you begin. So that is legal to do. And now you see this thing that's in the second parentheses here, 4x cubed plus dx, 4x cubed times dx. All of that together becomes du. And the first parentheses, that just becomes u. So we end up the integral of u to 6 du times 1/4. But here's something you need to be careful about. If we were just to leave this 0 and 3, those would be considered values of u, since this is a du out here. Well, certainly these are not values of u, they're values of x. So there are two ways to handle that. The way that I prefer most of the time is to do what we have here, and that is just to put an x equals in front of this. So we're saying that this is x equals 0 to x equals 3. We work it out in terms of u, substitute back in terms of x, which is what you do anyway when you're finding an antiderivative, and then evaluate it on those x values. An alternative approach is to actually take these x values and figure out what the corresponding u is, and then just put the values of u that go with them here and here, and you never have to switch back to x's in that case. Sometimes you might like that better. If you want to do it that way, that's totally fine. I will typically do my examples like the one here. So what we do that is now as we find an antiderivative, well, the antiderivative of u to the 6th du, that's just a power rule. So we add 1 to the power, makes that power 7, and then we divide by the new power. In other words, multiply by its reciprocal. So we can take 1/7 times 1/4 is 1/28. Remember, when you're multiplying fractions, multiply the numerators together to get the new numerator, multiply the denominator to get the new denominator. So we have 1/28 u to the 7th, and then we have to evaluate that from x equals 0 to x equals 3. To do that, I need to plug back in what u is, and so u is 3 plus x to the 4th. Replace the u by parentheses with 3 plus x to the 4th. Now what we have here is an antiderivative right here, and we just evaluate that from both ends. Notice in the antiderivatives we don't have to do the plus c. If we were to do it, we would just have a plus c here and a plus c here, but this minus would make that plus c in the second one into minus c. We'd have c minus c is 0. It's going to cancel out anyway. So you might as well just let it be 0. Any antiderivative will work in the fundamental theorem. So we do this, and what we do is we take this and we plug in the 3 in place of x, and we plug in the 0 in place of x and subtract those two. Now, this time I actually took, they both really technically should have had a 1/28 in here and here, but since that was in common as a factor, I used the distributive property to factor that out first. So let's see what we get here. 3 to the 4th is 81 plus 3 is 84, so we have 84 to the 7th. And then 0 to the 4th is 0 plus 3 is 3, so this is 3 to the 7th. And I actually, these both have 84 has a factor of 3, so I can actually factor out a 3 to the 7th, which I put on the numerator here, and that left 28 to the 7th here and 1 to the 7th here. Notice, let's just check it. 3 to the 7th times 1 is 3 to the 7th, certainly. 3 to the 7th times 28 to the 7th is 3 times 28 to the 7th. 3 times 28 is, yep, it's 84, so that's okay. 28 to the 7th, well, yeah, I used a calculator on that one. This big number right here. Subtract 1, we get this number. 3 to the 7th is 2187. And to get an exact value here was a little bit tricky. I had to take this top number and multiply it by this big one, and I actually had to get a calculator that would handle a number that big. But there it is, actually exactly right there. And it turns out, I checked it out, it does not reduce any. So this is the exact value, and here's a decimal approximation as far as my calculator will go using scientific notation. Now in a TI-84, you'd have a hard time coming up with that numerator. Not impossible if you kind of think about how it works, but not easy, not an automatic thing, because it's going to kick this into scientific notation and lop off some of the digits. So anyway, it is possible at least to come up with an exact value and a decimal value to as many digits as we want. Now how could you check this? Just enter it in like it looks right here on your calculator. If you've got a TI Inspire or a TI-84 with the new operating system, you just plug in the 0, push math on a 84, for example, you push math 9, and you get this. You plug in 0 here, 3 here, put in your formula right here, always put an X there at the end, and you should get this expression here, or something at least very close to it. Now, on the older operating system, this would be function integrate, then it's the function, comma, the X, then comma, the 0, then comma, the 3. And again, you should get that same thing. So that gives you a way to check that. Alright, let's try another one. Let's go up here and look at them again in case you haven't done it yet. Next one we're looking at right here is number 16. The integral from 0 to 2 of e to the x times the square root of 8 plus e to the x dx. If you haven't done that one already, please press pause and do that one now. Okay, so here's number 16. And here we have it. Here we have it worked out. Okay, well, let's see. I do see 8 plus e to the x, which is a variable expression, and then that's a square root on top of the whole thing, which is the same as a 1/2 power. So I could rewrite that part right there as 8 plus e to the x to the 1/2. So if I thought of the u as being that variable base, that's going to give me u to the 1/2. And if everything is all's right with the world, we can get get du out of this somehow. So let's see what happens. So if we let the u be the 8 plus e to the x, the derivative then is, well, the derivative of the 8 is 0, derivative of e to the x is e to the x, and then of course then you have the dx. So du is e to the x dx, and sure enough, there's the e to the x. Put it with the dx right here, and that part becomes du, and this part right here becomes u. So where did the 8 plus the e to the x go? It got replaced by u. Where did the e to the x times dx go? It was replaced by the du. Oh, now be careful. These are not u values for the exponent. They're x values. And by the way, there's something I should point out. We need to check this before we do any definite integral problem by the fundamental theorem. We first need to check to see if this function is continuous on this interval. Well, notice that e to any power is positive. So this part right here is a positive number. E to the power, e to any power is positive, plus 8 is a number bigger than 8, and so we're taking the square root of a positive number. E to the x, addition, square root, multiplication, those are all continuous functions, so this is built up out of continuous functions. They're all defined on that interval. I believe we've got a continuous function on that interval. You could also kind of graph it and look at it to kind of convince yourself of that as well. Okay, but we need to have that or we can't use the fundamental theorem. Okay, so here we go. Be sure you put x equals on these things when we do the substitution. Now we're just doing the power rule. So once we get this substitution, things look a lot better. Looks kind of messy at first. Substitution, now it looks pretty good. Add 1 to the power. 1/2 plus 1 is 1/2 plus 2/2, which is 3/2. Multiply by the reciprocal of the new power, 2/3, just times 1 is 2/3. And then we're going to evaluate it from x equals 0 to x equals 2. To do that, we're going to just substitute back in. Before I do that, I'm going to rewrite this in terms of radicals. Not because they're necessarily better, but just because that's the way it started with. Fraction powers are perfectly fine, but originally it had a square root. So notice 3/2 in mixed number form is 1 plus 1/2. So the power 1 is the u to the 1/2 is the square root of u. So u times the square root of u is u to the 3/2. Now I substitute back in what u is, which is 8 plus e to the x, both here and here, in place of the u's. And now we can actually do the evaluation, which is take the whole first function, plug in 2, and the whole same function, and plug in 0 in place of x. Notice that I actually factored the 2/3 out of the whole thing. Now, this was 2/3 times the u here, but then I said, well, that's just 2/3 times this whole thing, because I'm using the distributive property there to factor the 2/3 out front. So I did that right up kind of really when I went from this step to this step here. Okay, so where are we? Here we are down here, and we've plugged in the 2 for x here and the 0 for x here. Let's see if we can simplify. Let's start over here on the right side. E to the 0 is 1. 1 plus 8 is 9. And that gives us square root of 9, which, by the way, is just 3. E to the 0 is 1 plus 8 is 9. 9 times the square root of 9, that's 9 times 3, is not 18. It's 3 times 9, it's 27. And it's 2/3. Oh, I distributed to 2/3. So I was right to begin with. I sort of did 2 steps there. Where are we? Yeah. So I went ahead and multiplied the 2/3 out here. 2/3 of, well, this square root of 9 is 3, times the 2/3 is just 2. 2 times the 9 is 18, and that subtraction makes that a minus. So notice this 2/3 is not time. I got rid of this outer parentheses as well. So I did a couple things there. I took the square root of the 9 and then I distributed the 2/3. Now the 2/3 is still times this first part here. There's not really nothing you can do to simplify this other part. So there is our exact answer right here. Is this part right here. This is the exact answer right there. And if you plug that in the calculator, 2/3 times parentheses 8 plus e squared, close parentheses, times the square root of 8 plus e squared, then outside the square root minus, and that finishes up with 18. You can't see it on the screen right there, but minus 18. You get 22.24636997. How would you check that? Well, basically just enter in the original thing just like it looks. And that comes up with the same number, so we know that we did it correctly. Okay, let's do one more example. Excuse me. Okay, do number 17 now. Press pause. Okay, let's see if we can work this one now. You see we got 1 over 3x plus 1 from 0 to 1. Now we have to be really careful here when we have a fraction, because if we divide by 0, we have a discontinuity. To be able to apply the fundamental theorem, we have to have a continuous function over that entire closed interval. So, let's look at this. Well, let's see. The only place we would have a discontinuity is when 3x plus 1 equals 0. That's when x equals negative 1/3. Well, notice negative 1/3, excuse me, negative 1/3 is not in our interval from 0 to 1, and we know that rational functions are continuous everywhere they're defined. So this is a continuous function over that interval, so we may proceed with the fundamental theorem. Now, I think it's pretty obvious the only thing we really got that would be something to try is to let u be the denominator. So if we let u be 3x plus 1, then du is just 3dx. Once again, we do this little trick of where we insert the 3 with the dx here, but we balance it by putting its reciprocal out front. As long as that's a constant, that's legal to do. So now the part in the parentheses, 3dx, becomes the du, and the fraction becomes 1 over u. And again, these limits are x limits, so I'm going to write x equals 0 to x equals 1 when I write down that definite integral. Now, the antiderivative of 1 over u du is the log of the absolute value of u. That's the natural logarithm, ln. And it's evaluated from 0 to 1. I still have my 1/3 out front. And actually, I guess technically the 1/3's in here, but we can factor it out front here as well. So I'm just going to bring it out front here. Make sure I put parentheses around the whole thing, though, here. The u is then 3x plus 1, as we saw up here. And so then we just substitute in a 1 and a 0. Well, let's see what we can get out of this. 3 times 1 is 3, plus 1 is 4, so that's the natural log, and the absolute value of 4 is 4. So that's the natural log of 4. 3 times 0 is 0, plus 1 is 1. Absolute value of 1 is 1. The natural log of 1 is 0. So we have log of 4 minus 0 is log of 4, times the 1/3 is 1/3, natural log of 4. Log of 4 is 2 to the second power. 4 is 2 to the second power. So we can bring the power out front using a property of logarithms and write that as 2/3 times the natural log of 2, which is probably one of the best ways to write our final answer, which is our exact answer. Then you can plug 2/3 times the natural log of 2 in your calculator to get a decimal approximation, and notice that when I do this one in the calculator, it does check out to give us the same value. So that gives you some more examples, and hopefully that will help you get better and better at this. You need to do lots and lots of problems where you're finding these antiderivatives, problems where you find the whole family of antiderivatives, problems where you find a specific antiderivative given a specific value of a point on the graph of the function that you're looking for, and you need to be able to find some definite integral problems, and all of them come down really to finding the antiderivative of the thing you're integrating here, okay, and that's going to be using these integration rules that we talked about back here a little ways. where we looked at these. Let's see, where are some of these problems? Here's our kind of our list. Okay, and we can work through. Here's the list right here. And notice, remember, they all came from a derivative rule over here on the left. Gives us an antiderivative rule or definite integral rule on the right. In particular, you've seen in these last couple of videos problems where we did integration with substitution. So we're basically doing substitution to get it to be essentially really not that many things we know how to do thus far. We'll add to this a little bit in the next few videos, but basically we're looking at u to what you've done your substitution, where the variable u is to a constant power n. If n is not -1, you get the power rule here. If n is -1, you get this logarithm for an answer. Or we're getting e to the u, or in general b to the u. we know how to do basically exponentials and power functions are the main two things that we know how to do. Now, we are going to, in the next video, talk more about this product rule backwards, which is called integration by parts, and we'll pick up with some examples of that in the next video.